Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into metrics and monitoring, the observability backbone that keeps every production system sane at scale. We'll cover how cloud-native platforms collect time series data, build dashboards, trigger real alerts, and control cardinality. Whether you're preparing for a senior engineering interview or building observability infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into metrics and monitoring, the observability backbone that keeps every production system sane at scale. If you have ever wondered how companies like Netflix, Google, or any cloud-native platform collect billions of time series points, build dashboards in Grafana, page engineers on real alerts, and control cardinality explosions, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building observability infrastructure, let's get into it. Here is the core problem. A modern distributed system has thousands of microservices, containers, queues, databases, and edge locations. Every component emits logs, metrics, and traces. Engineers need to know if the system is healthy, where latency is coming from, which errors are customer impacting, and when to wake someone up at night. But without a metrics and monitoring platform, teams are either flying blind or drowning in noise. A missing metric means you detect an outage only when customers complain. A misconfigured alert wakes the on-call engineer for every minor blip. A cardinality explosion silently crashes the time series database. A slow dashboard makes incident response painful. The business needs a unified observability platform that ingests, stores, queries, visualizes, and alerts on metrics in real time. Let's walk through the functional requirements. First, the system must ingest metrics from many sources: application instrumentation libraries, host agents, cloud provider APIs, Kubernetes, message queues, databases, and custom exporters. Second, it must store time series data efficiently with support for timestamps, labels, values, and retention policies. Third, it must provide a powerful query language so engineers can aggregate, filter, and compute rates, percentiles, and ratios across tags and time windows. Fourth, it must offer dashboards and visualization with charts, heat maps, tables, and annotations for incidents. Fifth, it must support alerting with threshold, anomaly, and composite rules, plus routing through PagerDuty, Slack, email, or webhooks with escalation and silencing. These 5 capabilities turn raw numbers into actionable observability. Now the non-functional requirements. The system must be low latency for both ingestion and querying. Dashboards should load in seconds even during incidents, and alerts should fire within seconds of a threshold breach. The system must be horizontally scalable, because a large platform can emit millions of metrics per second. The storage must be cost-efficient since time series data is high volume and mostly write-heavy. The query engine must be highly available, because engineers depend on it during outages. The alert pipeline must be reliable. A missed page is an outage that drags on, while a false page destroys trust. Data retention and downsampling must be configurable so hot data stays fast and cold data stays cheap. And finally, the system must be observable about itself so you can monitor the monitoring system. Here is the high-level system architecture. On the left, agents and client libraries running inside applications or on hosts push or pull metrics through a load balancer and API gateway. The ingestion layer validates, normalizes, and enriches each sample with metadata, and then writes it into a distributed time series database. A metadata service keeps track of metric names, label sets, and cardinality. A query engine handles PromQL style queries, reads from both hot and long-term storage, and serves the dashboard and API. The dashboard application renders charts, variables, and panels. An alerting engine evaluates rules on the query results, deduplicates notifications, and routes them through channels like PagerDuty or Slack. A long-term store, often object storage, holds downsampled or archived data for capacity planning and compliance. The key metrics to memorize cold. Ingestion rate, measured in samples per second, tells you how much telemetry the platform is absorbing. Query latency, especially the 99th percentile, determines whether dashboards are usable during an incident. Storage cost per sample, which drives the economics of retention. Cardinality, the number of unique time series, which is the silent killer of TSDB performance. Alert latency, the time from a problem starting to the notification being sent. Alert noise ratio, the fraction of alerts that are real versus false or informational. And mean time to detect and mean time to recover, the business-level outcomes that justify the entire observability investment. These metrics are what the business actually cares about. Let's trace the end-to-end user journey. A site reliability engineer is on call for a payment service. She opens the Grafana dashboard and sees the error rate panel turn red. She drills into the region dimension and notices US East has spiked. She opens the logs and traces correlated with the metric, identifies a failed deployment, and rolls back. Meanwhile, the auto alert triggered by a Prometheus rule fired into Alert Manager, which routed a PagerDuty page to the on-call rotation, and posted a Slack thread with the relevant runbook. After the rollback, the metric recovers, the alert automatically resolves, and the postmortem is scheduled. The entire loop from detection to recovery happens in minutes because metrics, dashboards, and alerts are tightly integrated. The core models and algorithms. The data model is the time series itself. A metric name, a timestamp, a value, and a set of labels or tags. Cardinality is the Cartesian product of those label values, and it must be controlled through careful label selection and limits. The metric types include counters, gauges, histograms, and summaries, each with different aggregation semantics. The query engine uses an inverted index or a label index to find series quickly, then scans compressed time windows. Downsampling reduces resolution over time to save space. The alerting model evaluates expressions periodically, maintains state, and deduplicates notifications. Retention and compaction policies balance granularity with cost. The key trade-off is precision versus cost. More labels and higher resolution give better visibility, but explode storage and query cost. Now the low-level design deep dive. The ingestion path is implemented as a write-ahead log or commit log that replicates samples across nodes before indexing. The index store maps each label value pair to the matching series IDs, often using an inverted index or a key value store. The sample store compresses values using delta of delta and XOR compression for timestamps and values. The query planner parses PromQL, expands selectors against the index, fetches chunks, and evaluates aggregations in parallel. The alerting engine maintains a rule evaluation loop, compares results against thresholds, and emits alert events to a notification router with grouping, inhibition, and silencing. For multi-tenant deployments, isolation is enforced through per-tenant limits, separate cardinality quotas, and authenticated query paths. The whole system is designed for high write throughput and read time aggregation. Key takeaways for your interview. First, metrics and monitoring is a time series data problem at its core, so expect questions about indexing, compression, cardinality, and retention. Second, separate the ingestion path, the query path, and the alert path because each has different scale and latency requirements. Third, cardinality control is not optional. Interviewers will ask how you prevent a bad label from taking down the database. Fourth, alerting is about signal to noise, so discuss threshold tuning, anomaly detection, grouping, and escalation from the start. Fifth, dashboards and alerts are only useful if they correlate with logs and traces, so mention observability pillars and unified incident response. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for metrics and monitoring. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on metrics and monitoring. We covered the full picture, from ingestion and time series storage, through query engines, cardinality control, alerting, and the low-level design of the TSDB and alert pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.